So, good morning everybody, welcome back to mobile communications. The last time I told you a little bit about the motivation, a little bit about the history of mobile communications, and today I will start with the very basics, wireless communications. Wireless communication sometimes is a little bit strange, unknown territory for computer scientists because there's something going on that is typically, well, issue for electrical engineering, waves, electromagnetic waves, and I will not go into the details of any, formula about electromagnetic waves or all these things, but you should get a basic understanding of how electromagnetic waves behave. Well, basically, this is something you might have learned during high school in physics. There are some nice experiments with lasers and diffraction, refraction, and all these things. And similar things happen to these electromagnetic waves we use in wireless communications. So today, something about frequencies, signals, antennas. We need something like antennas. Well, basically, we use a light bulb to emit light, and we use an antenna to emit other electromagnetic waves, and this is quite similar. You will learn a little bit more about MIMO, cognitive radio, software-defined radios, modulation, spread spectrum, the very basics, so that you can understand why do we have something like 200, 400 megabit per second over the air today with a tablet compared to some kilobit per second we had last year with whatever wide area mobile communication system. Okay, so first of all, what we need are electromagnetic waves. Here you see what we call the spectrum, a spectrum of electromagnetic waves. And be aware, this is a logarithmic scale. What does it mean? You see here on the x-axis 300 hertz and 300 megahertz, 30 gigahertz, terahertz, 300 terahertz, whatever. So frequencies of electromagnetic waves. And you also see wavelengths. Typically, when we talk about visible light, which is here, visible light, we talk about wavelength in the range of 1 micrometer, 850 nanometers. So, well, if you talk to someone, usually you use other terms. You say red, blue, green. You don't say, oh, these, the leaves out there in the trees, they are really pretty 650 nanometers or whatever. So you say they are green, whatever. Yeah, I hope this is green. So we use colors, but that's nothing else but a certain frequency in the range of visible light. We are aware of ultraviolet light, and then we have X-rays, cosmic rays. We usually don't use them for communication. And it starts to be a little bit dangerous when we go here towards, let's say, X-rays, etc., because they can destroy cells in your body, etc. Usually we say, okay, the lower frequencies, they are not that dangerous when it comes to, if you think of cancer and all these things. So this starts when we go to X-rays, to higher energies. So we use visible light for communication. That's a very traditional way of signs, signaling something, smoke signals, etc. But also today, visible light communications, the light we emit from LED light bulbs, and we can modulate it. So pretty high data rates. We use infrared, that's what you know from all the remote controls for TV sets. And if we talk about most of our wireless communication systems, they use frequencies, well, roughly here we have the 2.4 gigahertz, for example, of our wireless LAN. We have the 900 megahertz of our GSM mobile phone system. We have the whatever frequencies of our digital television, etc., etc. So these are the ultra high frequency, super high frequency ranges. In former times, we also used lower frequencies. Still today, submarines, they use very low frequencies. Why? Well, if you're into diving, for example, you notice, well, the first meter, oh, everything is colorful. After 5 meters, well, blue. After 10 meters, dark blue, and then it becomes darker and darker and darker. So higher frequencies, they cannot really easily penetrate water. Low frequencies, they can. And we also have a different behavior if we go to higher frequencies. For example, light cannot penetrate wood, but it can easily penetrate glass. Light cannot penetrate this concrete wall, but you can use a mobile phone within this room. So somehow these low frequencies, they can penetrate concrete. The question is why? So it's not that easy to understand why can light penetrate glass. Well, we also, glass, you can look through glass, but why? That has something to do with electrons, the crystal structure of glass, etc., etc. But here it's just to show you from a physical perspective, there's no difference between visible light, our electromagnetic waves, or terahertz waves. Terahertz waves we can use to look through walls, for example, to detect people in a room. That's used for detecting people when some people have hostages, for example, and so you can look through people. Also, we use 60 gigahertz, for example, to scan people at airports. So we can detect certain things carried, so like explosives, for example. So different frequencies for different purposes. Okay, and if you look at this very, very, very simple formula, you see it doesn't matter if I talk about frequencies or wavelengths. So, frequency time wavelength is the speed of light. So that's very simple relation. Speed of light, approximately 300,000 kilometers per second. 300,000 kilometers per second. That's not that easy. What does it mean? Well, it takes 8 minutes to the sun, or much simpler to remember, 30 centimeters, that's equivalent to 1 nanosecond. 1 nanosecond, 30 centimeters. Why is this important? Wavelength, the speed of light, etc. Because, as we will see, the wavelength directly influences the size of the antenna. The speed of light, differs depending on the medium, which results in, as we will see, many interesting effects. So first of all, these are the frequencies, and usually for communication, we use something here in between. We have some communication around 60 gigahertz, and now here the VLC, visible light communications, here at visible light, what we can receive with our eyes. So you see, if you have a radio receiver or your eyes, both are receivers for electromagnetic waves. So there's nothing special about light or this or that. So it's just a different wavelength, different frequency, or different energy, so to say. Okay, so these are the frequency ranges what I just explained, like what we use here for wireless LANs. And also you see what we can also use it here for the microwave oven. Yeah, that's also at 2.4 gigahertz. And even, you have today nicely shielded microwave ovens, but if you switch on the microwave oven and you have a wireless LAN close by, there's still a lot of interference. Because wireless LAN operates at whatever 100 milliwatts, a microwave oven operates at 900 watts. So big difference. So a huge factor, and so even if you shield your microwave oven, it still emits a fraction of these electromagnetic wave to the environment, and this causes a lot of interference. And we have many effects, as I will show you, like so-called weather-dependent fading, so you weaken the signal. You weaken the electromagnetic waves depending on the weather, as we will see. So different ranges for different purposes. The higher the frequency, that's something you can remember, the smaller you can build the antenna, because usually the antenna size depends on the wavelength. This is why submarines, for example, they have very long antennas, and they carry the antennas, and you see them, they can be hundreds of meters long to receive something. Okay, that's not very practical for your smartphone. That's pretty sure. Okay, and so to make it a little bit more confusing, though, to make the picture clearer when it comes to the frequencies we use for our mobile communication system, this table shows examples. Examples for cellular networks. That's where we have our, for example, our normal mobile phones, so UMTS systems, 3G systems, or 4G systems, whatever. So cellular networks, and you see many different frequency ranges. Why do we have different frequency ranges? Well, there are historical reasons. Historical reasons, Japan, as an example, is an island. So they can decide on their own, oh, we use this or that frequency. Okay. Europe and USA, also for historical reasons, use slightly different frequencies. Why? As we will learn, it's organized in different ways. So the classical scheme in Europe was the governments decide which frequency to use for which technology. In US, typically the decision was, okay, we use this frequency for a certain purpose, and then we let the market decide which technology to use in this frequency. So, and the result is, as you see, for example, in the US, you have different competing technologies at the same frequency. In Europe, you have a clear separation for these different technologies. You will not find two competing technologies on the same frequency. So that's a different philosophy. I will then give examples why it might be better to have this separation in chapter 4, but it's different philosophies behind it. And you see, it's a little bit different when we come to wireless LANs. Wireless LANs, we have more or less the same frequencies worldwide. That makes it much easier to develop hardware, use more or less the same frequencies. You see, we can use a little bit more frequencies in Europe compared to the US. These are the channels 12 and channel 13 in the wireless LAN, for example. But it's more or less the same. That's the so-called ISM band. This exactly where also the microwave ovens operate at 2.4 gigahertz. So that's one of the so-called industrial, scientific and medical ISM bands where you can operate devices without having a license. In other frequency ranges, it's heavily regulated. You have to buy a license. For example, in the UMTS ranges, as we will see, the network operators bought the licenses only for Germany for 50 billion euro. And at the ISM band, you can just buy a microwave oven. And no one cares, you don't have to buy a license to operate it. But for the other bands, the operators, the network operators bought the licenses to use the frequencies. Because all these frequencies usually are regulated. In Germany by the Bundesnetzagentur. And they say, okay, these are frequencies for GSM, these are frequencies for LTE, for digital television, for military, for astronomical purpose, for scientific purpose, for this and for that. So it's regulated. You cannot simply start your own sender on any of these frequencies. And then there are many other radio frequency systems, garage door openers, whatever frequencies, for example, to detect goods you buy in a store, these so RFID tags you have on clothes and on whatever objects to prevent that you simply steal these things. So many different frequencies for different purposes, and from time to time there are auctions, worldwide auctions, and a lot of discussions going on which frequencies to use for what purpose, because this requires a lot of planning. Some of the frequencies are still used by older technologies. We have the situation right now in Germany. Maybe you heard that it starts now and it continues till next year. The classical, so to say, digital television will go away. The DVB-T will be replaced by DVB-T2, operating with a different technology on different frequencies. So you have to buy new devices. And then we can reuse the frequencies. Also, we don't have any analog TV anymore, replaced by digital systems. Or frequencies you can now reuse for LTE, for example. LTE, and there was also a process where the government actually sold the frequencies to companies, to network operators, that they can reuse these frequencies in Europe these 790 to 821 megahertz frequencies. So you have regulation, and then you have a lot of physical effects. I mean, yes, we could use, hey, there are frequencies around 100 gigahertz. Great. Yes, but you cannot use them, for example, to penetrate a wall. So you cannot use them for mobile phones. Or, so there are some physical effects why you cannot use this or that frequencies. Either they are blocked by other applications, or physics says, no, you cannot use them because they cannot penetrate a wall, concrete, this or that. Then sometimes you have problems in manufacturing, designing receivers and transceivers. It's not that simple to create the hardware for certain frequencies. It's simpler for some other frequencies. So there are a lot of limitations. Okay, so just to show you many different frequencies. The basic principles are always the same. And later on you will see that telecommunication systems we place on top of all these physical layers, they don't care in the end. So today you have, for example, in the GSM technology, you have the quad band transceivers, so they can operate on 4 different bands. The 2 bands we use in Europe and the 2 bands used in the US, for example, for the GSM technology. Okay, and similar as true for you. Okay, so to start with the basics, now we know we have certain frequencies we can operate on. But what is this electromagnetic wave? So in the end, as you hopefully have learned in telematics, in the end, we have to represent data. So somehow we have our ones and our zeros, and we have to translate them into something we can transmit in the end over the air. In telematics, you learned, yes, we have to translate this into something we can transmit over the cable, over fiber optics, over copper wire, twisted pair, coax, whatever cable. And now we have to transmit this over the air somehow. And we know we can manipulate certain parameters with these signals. Amplitude, frequency, phase. And this is exactly what we also use here in wireless communication. We learned, and this is just to repeat again, we have analog and digital signals. So analog, that's what nature usually does. So continuous time, continuous values. That's when I speak. That's whatever when you modulate some natural signals like light, or if you have a candle or whatever, analog. But we know in our computers, we operate with ones and zero, with discrete values, and that's what we can generate. So we will see how we can generate our analog signals we transmit over the air based on our digital values and our digital signals. Basically, that's one of the very few formulas you will see. We can think of a nice sine wave, very simple sine wave. And now, depending on our data, when we can change the values for the frequency, for the phase. Phase, as I will explain, is how we shift our signal with respect to an original signal. We'll see what phase means, and the amplitude. So how strong is the signal? And we see advantages and disadvantages of these different ways of manipulating our signal. There's also something I explained in a little bit more detail in telematics. Remember, yes, that's something we're used to from computer architecture. We have ideal signals inside the computer. Yes, the 1 is 5 volts, 0 is 0 volts, for example, or 1.3 volt and 1 volts for the logical 1 and the logical 0. And already in telematics, I told you it's impossible to transmit these ideal periodic signals. There I showed you what happens if you have that ideal medium. And here, if we transmit over the air, that means over, space, without using our antennas, we'll see we have even more restrictions. I already told you the antenna size pretty much depends on the wavelength. So that means if I create a mobile phone that should fit into a pocket, I should use electromagnetic waves with frequencies that somehow fit to small antennas, because I'm not a submarine, so I cannot have a long antenna. That's what I told you the last time about Marconi. They created these 100 meter high antennas, and then they could transmit something. We also learned in telematics that basically, if we try to transmit this ideal signal, it's a composition. We can think of it as a composition of these many so-called harmonics, many sine waves with different frequencies. So you see, if we try to transmit something like this ideal signal, and well, we can think of it as a composition of these harmonics, depending on the transmitter characteristics, the antenna, the hardware, the medium the waves should penetrate, we are all able only to transmit a part of this signal, which is not nice. So in the end, we can never transmit this ideal signal. If we think of, okay, there are many of these, it's a composition of these sine waves, and based on the medium, we can transmit only certain frequencies. Then we can never transmit this ideal signal, but it will be some strange, bizarre, distorted signal. So it's quite obvious that we cannot transmit this ideal signal. So we have to translate our ideal signal or our ones and zeros into something we can transmit over the air. Now this is even more important compared to these wired systems. For wired systems, we could still think, okay, let's try to transmit these rectangular shaped signals. Let's see what happens. Over the air, it simply doesn't work. Antennas cannot transmit this. They will not do it. And if you want to penetrate a medium, like a wall, with these signals, only a small part of the frequencies can really penetrate the wall, and the wall actually filters out all the other frequencies. Okay, so how do we then transmit our ones and our zeros? Before we go into these details, we have to learn, partially repeat, the representation of these signals so that you can understand when I talk about constellation diagram, what does it mean? So basically, we can represent a signal by the parameters, the amplitude, the frequency, and the phase. And if you look at something that's called an oscilloscope, you will see the signal shown as the signal, well, over time on the x-axis, you see the amplitude. That's nice to see the sine wave. That's what you, if you have an oscilloscope. So that's what you use, for example, in physics. If you look into a device like an oscilloscope, you see the sine wave. And this is nice to explain something like the phase shift. So if we shift the sine wave a little bit in this, what we call the phase, then we can code our ones and zeros into this phase shift. Okay. That's nice for a single nice sine wave, but if we have composed signals, composed of many different sine waves, it's you will not see anything anymore in an oscilloscope. Last time I showed you a spectrum analyzer to show you the whole frequency range, in this case between 0 and 6.7 gigahertz. And we looked into what a wireless LAN does, Bluetooth. Do you remember? I showed you this in a spectrum analyzer. A spectrum analyzer has on the x-axis the frequency. And if you have a single sine wave, this is then a single peak at a certain frequency. So if you have a sine wave of 1 kilohertz, you see a peak here at 1 kilohertz. If you have a second sine wave here, then you see a second peak, a third peak, etc. So this in the end gives you the spectrum, the so-called spectrum of a signal. There you see the decomposition of the signal. Basically, it's an inverse Fourier transform and a Fourier transform. These are the mathematical tools to translate from the time domain, that's what the oscilloscope shows, into the frequency domain. That's what the spectrum analyzer shows. So that's exactly what a spectrum analyzer does. It's a Fourier transform. That's basically all. That's also a way of showing different, well, parts, different components of a signal. Also to show, for example, different channels. If I explain later on telecommunication system, I will talk about channels, about frequency multiplexing. Then I will always go into this way of displaying signals. I will show you the spectrum. There we can see, oh, we have one channel here and we have another channel there. and then we do frequency division multiplexing. This is something I cannot show in the time domain. So, but this is something I show here in this frequency domain in the spectrum. That's just ways of how we can actually, well, display, show, describe signals. Then there's a third way, not that easy to understand, just a third way of showing, okay, that's also a signal. There we use a vector with a certain length. That's the strength, the amplitude of the signal. So the longer the vector, the stronger the signal. And an angle. The angle here, that's our phase shift. And then we can display a certain point in this diagram, and this is so-called a constellation diagram. And there we have a certain point. And I showed you this in telematics when we talked about modems. I showed you how you can code, for example, 4 points in the constellation diagram, and then you assign digital values, for example, 1, 0, 0, 0, whatever, 1, 1, and here we have 0, 1. You assign digital values, in this case, 2 bits per point in our constellation diagram, and this is exactly what modems do for wires. And that's the same we do here for the wireless domain. But well, it's a little bit more complicated because we have a lot more interference, but basically it's exactly the same. So these are just 3 ways of showing what's going on when we look at signals. So the time domain, well, yes, we can show a little bit the phase shift, but usually we use the frequency domain to show the different channels of Bluetooth, of a wireless LAN. And we show the constellation diagram quite often when we show how to code bits onto a signal. So that means, in the end, if I transmit something like 0011, then it means that my nice signal, like this, suddenly has a phase shift here of 180 degrees. Why? Because first I transmit 0, 0, and then 1, 1. And going from one point in the constellation diagram to this other, that's exactly a phase shift of pi or 180 degrees. So yes, I can also show this. This would be in the time domain. So here we have the time on the axis. But it's exactly the same. So we have a nice sine wave and suddenly a phase shift of 180 degrees. And this is how we code the code word 0, 0 and then 1, 1. Just different ways of explaining what happens there. And usually a constellation diagram is easier to understand if we have hundreds of points there and to show what does interference mean, etc., etc. And the spectrum, so the frequency domain, is typically used when we talk about channels. So depending on what we want to talk about, we use different ways of displaying what a signal is. Okay, so that's what you should remember, because this is what I will use throughout the course. If I say, okay, these are our wireless LAN channels, then you should remember, okay, that's the frequency domain. Okay, that's just the frequencies on the x-axis, and now we have to separate different channels, for example. So nothing wild, just a way of displaying it. Okay, now we know we need frequencies. We know a little bit about how we, well, actually display this with different ways of different diagrams. Now what do we need? We want to emit and receive electromagnetic waves. What we use for this are antennas. For visible light, we use a light bulb, a light source like a candle or LED light as a transmitter, and the receiver is, for example, our eye. Well, okay, here we call it antennas. That's for different frequency ranges. Our eyes are for the terahertz range, what we call light. And here we use the antennas. And in the end, we want to radiate and receive electromagnetic waves. Okay, so basically, that's a transition for the wave from a cable, piece of copper, into space. We don't need the medium. Just to repeat this, we don't need a medium. And now real antennas, they have a different behavior. And you should at least know what is the typical behavior of a normal antenna. And we always compare the behavior of a real antenna with something we call an isotropic radiator. Isotropic radiator, that's basically something theoretical antenna. It doesn't exist in real life. That's just a point in space that emits electromagnetic wave. And if you think of a point in space emitting waves, it's like one wave front looks like a balloon. And you blow air into the balloon, and the balloon grows and grows and grows and grows and grows. And the wave fronts are then many of these balloons just originating at this theoretical point in space, and then you can think of these balloons emitted by this simple point. And that's only used for comparison. And then we can draw the so-called radiation patterns, a radiation pattern. The radiation pattern basically measures the radiation around the antenna. All the antennas, they emit the electromagnetic waves, they radiate, so they are radiators, and they emit the waves, and we always compare with this ideal isotropic radiator. Isotropic because the strength of our wavefront, so the strength of the antenna, of the wave, the amplitude of the wave, it's always the same depending on the distance to this isotropic radiator. Real antennas, they have what we call directive effects. And we will see we use them. Directive effects, what does it mean? A real antenna has a stronger, what we call beam, in a certain direction. So we can direct, it's like a flashlight you can hold in your hand. It's not an isotropic radiator, but a flashlight shines the light in a certain direction. That's exactly what we use usually. The isotropic radiator radiates in all directions, the same strength. So, but that's just a theoretical construct. Real antennas, they look different. Real antennas, well, that's exactly what Heinrich Hertz used. 1886, more than 100 years ago. Simple antennas, and they are not isotropic radiators, but you have to build them somehow. And the very basic design of an antenna, that's also called a Hertzian dipole, is shown here. And the ideal size of the antenna, what does ideal mean? That's the best dimension, the best shape for the antenna to emit as much energy as possible, is exactly when the length of this antenna is lambda half, so half the wavelength. Okay, so, and this is why the wavelength, that means the frequency, directly influences the size of the antenna. Think of lower frequencies. Lower frequencies have huge wavelength, that means huge antennas. So for long wave systems, you need these 100 meter high antennas. And for today communication system, well, you have some millimeters of antennas. Plus today you have a lot of electronic help for the antennas, but that's just the basic design of a so-called Hertzian dipole or dipole with lambda fourth. That's what you see on the roof of a car, for example. If you have a car, you see quite often these short antennas somewhere. That's exactly, these are lambda fourth antennas. Now you might think, but I can receive different frequencies with it. Yes, but the antenna is perfect for a certain frequency and more or less okay for frequencies close by. So this is why we have one antenna for classical FM radio, but a different antenna, for example, for GPS, and different antenna for LTE. But you could reuse the same antenna for GSM and LTE if the frequency ranges are close by. They are not optimal, but okay. And you can fine-tune with some electronic help these antennas. But these are the classical antenna designs. And if you look at the radiation pattern of this simple Hertzian dipole, you see, oh, there are more these donut-shaped things. So if you look at the antennas, the wavefronts are not the same in all directions, but it's more or less you emit wavefronts like this, and the further away you are, then they are more like these wavefronts here. But if you look along the z-axis here, this is the y, in this case the y-axis here, you do not emit energy in this direction. Why is this useful? Well, think of an antenna as we have it back there for the hotspot here of the wireless LAN. It doesn't make sense to emit energy into the ceiling or into the wall, for example. But those antennas should emit the energy, most of the energy, towards your laptops and your mobile phones, and not into the ceiling. Because what happens in the ceiling? Well, the ceiling absorbs the energy, is heated up a little bit, and that's it. So, useless. So, most of the technical antennas we use, they are directed. And that's for a good reason, because you want to direct antennas, for example, on the street, where people are. So, directed antennas. So, and there we also talk about the antenna gain. Antenna gain, it's the maximum power in the direction of the main lobe, as we call it. So we form a beam, and those beams, they have a certain lobe. And this is the gain is the maximum power in the direction of the main lobe, compared to the power of an isotropic radiator with the same average power. So you put a certain amount of energy into your theoretical antenna, you put the same amount of energy into your real technical antenna, and then you measure, let's say 10 meters away, what is the energy you receive from your theoretical antenna, and what is the energy you receive from your real antenna. And then basically the gain is then the maximum power in the direction of the main lobe. And you try to have, for example, your main lobe towards the street where people are, or in a tunnel, for example, for the subway, not into the wall of the tunnel, but towards the subway, or where the subway could be. So this is why you need those directed antennas. And that's exactly what we also see everywhere. For example, what I said, on the wall, we have directed antennas that try to have their main lobe towards you here in this lecture room. Or we have antennas for so-called sectorized antennas for base stations. So for base stations, you usually see the antenna pole, and then you see antenna slightly tilted down, for example, towards the road. And the main lobe then should go towards you walking somewhere on the road or towards the cars, and not directly into the roofs of other buildings. Doesn't make sense. So it's slightly tilted, for example. You can either do this in a mechanical way or in an electronic way, this tilting of the antennas. So this is what you see quite often on these base stations of mobile phone systems. Quite often you have so-called sectorized antennas, so you have 3 antennas in one antenna pole, 3 times 120 degrees to cover the 360 degrees. So that's where you use this. So if you want to cover a valley, you use these antennas with the main lobe down into the valley. That's the idea. Or we also all know this from is satellite dishes. Well, a satellite dish tries to receive the signals from space, and on a satellite you also have a small dish that is directed down to Earth and not into outer space. So an isotropic radiator on a satellite, that's not very brilliant. So you have these directed antennas there as well. So especially for microwave connections or microwave 60 gigahertz for, connections, etc., as I will show you, you need these directed antennas. But then for mobile phones, yes, it's nice to have directed antennas for the base station, but if you look at the mobile phone, it's a little bit more difficult. Because the mobile phone might be on the table, might be tilted somehow. Usually it's somewhere close to the ear, maybe not, depending on if you have a headset, etc., etc. So if this were purely directed antennas, we would have a problem. So it depends on the use of the antenna, if you want to have this directional behavior or not. But partially we have this directed behavior. So also for mobile phones, because usually you have it on the ear and then depending on the base station, etc., etc. I will show you the pictures for that. Okay, antennas. we will not go into the details of antenna design. You should just get a basic feeling of, okay, we need antennas. Without antennas and without radiation of electromagnetic waves, no mobile communication. So they always radiate. So now what can we do with antennas? And this is something that came up, military use, decades, for civil use since some years. We can use more than one antenna. One antenna is okay to receive something, but what happens if we use more than one antenna? So we can integrate, for example, 4x4 antennas, so 16 small antennas on a mobile phone or on a tablet or whatever. Why? We can use something that is called diversity. Here the technical term diversity means we use 2 or more antennas that can receive signals in a constructive way. So we can use it in a very simple way, so-called switch diversity. So signals, for example, reach the antenna from one sender, they reach the antenna, but maybe due to whatever obstacle, the signals are attenuated. Signals one of the antennas receive. So we can automatically switch between the antennas. And now we can use one antenna with a better signal quality. Okay, that's very simple to do. That's called switch diversity or selection diversity. So you choose the antenna with the largest output power. Simple. Okay, what is used today is so-called diversity combining. What happens there? If we have our base station here, base station sends signals. The antennas, they receive the signals. Let's assume they all receive the signal with different strength, different attenuation. So weaker signal, stronger signal, that's one thing to handle. The second thing is, what else could be a problem if you have a situation like this? Can you imagine a problem? Now you receive the signals, okay? The signals you receive, analog signals, they travel along this wire and you recombine them. What could be the problem here, where I simply have this plus sign? Yeah?
They could be out of phase.
Yep, exactly. They could be out of phase. What does it mean? They experience different delays. So there's some delay 1, there's some delay 2, there's some delay 3. Why? Just let's assume they all have what we call a line of sight. So a direct line of sight means direct visible connection between sender and receiver. Even in this situation, you see that delta 3 is larger than delta 2, is larger than delta 1. Why? Because we have a limited speed of light. And now if you assume we have this 30 centimeters is 1 nanosecond, which is only true in vacuum. We don't live in vacuum, but okay, let's assume 30 centimeters, 1 nanosecond. If we now have the antenna spaced apart for some centimeters, this means a phase difference of some dozen, 100 picoseconds. You might think, okay, come on, picoseconds, who cares? Think what happens. I mean, we are operating at whatever, 2.45 gigahertz. 5 gigahertz. 1 gigahertz already means a wavelength. 1 gigahertz means one transition in your sine wave in 1 nanosecond. So you see how nice this all comes together. So 1 nanosecond, your sine wave already travels in one period 30 centimeters. So you see, you can really make this visible, the phase shift. If you have your antennas some centimeters apart, you have already some phase shift, some centimeters, which is reflected in some degrees of your nice sine wave. So if you want to recombine, you have to adapt the power. So they have different power, so you have to adapt the power, you have to amplify them, but also you have to insert certain delays here. Certain delays for the different signals. And then the signal that arrives first you have the delay a little bit longer so that you can recombine them in a constructive way. Because otherwise, they cancel out each other. That's a problem. And that's exactly, for example, what your mobile phone does. Your mobile phone with several antennas receives all the time signals with different phase shift and has to recombine them in a constructive way. That means delaying a little bit more, a little bit less, etc. How we do this, I will explain later on why and how. So, first of all, we are at antennas, so diversity combining. So we need something that's called a co-phasing. So we have to bring all together again in the same phase, or at least the strongest parts of the signal. Now this looks like, okay, the base station emits 3 signals. No, you have to always think of these are wave fronts, and part of this wave front is received here, received there. And this is only for the very simple scenario with only line of sight, direct visible connection between the receiver and the sender in vacuum. We don't live in vacuum, we have buildings, we have many different things. You will see real life is a little bit more complicated than this. But this is why we use several antennas, and that's exactly what we do today also in all wireless LAN routers. Your DSL routers at home, we do exactly this. We use several antennas. And this is why sometimes it's even visible. Some of the routers, you even see the antennas on the outside. For mobile phones, for example, usually it's not visible. So it's somewhere inside. You don't see those multiple antennas. For military systems, you have hundreds of these antennas because you can do many more interesting things. You can also use it the other way around to create interesting signals. Yeah?
Why is okay, ich krieg's das Englisch nicht zusammen. Warum ist die bei der Dreierkonstellation, warum ist die Antenne kürzer?
Here, why is this lambda half, lambda fourth? This question, because we don't have this ground plane. These are just examples. So if you have the ground plane, the best design for these antennas is that you have a length of lambda fourth, this short antenna, and these are those Hertzian dipoles. So these are freestanding antennas, free in space. They don't have the ground plane. So if you have a ground plane, the best length is lambda fourth. If you have no ground plane, you have lambda half as classical antennas. We only talk about classical antenna design. Look up Wikipedia or any other literature about antennas and you will find many more. But good question, so why lambda half? Because these are the classical Hertzian dipoles. They are lambda half apart and they have a length of lambda half. Here it's just an example with the ground plane. We could also do this with the ground plane. Different antenna design, different ways of designing antennas. Okay, that's a reason why we have to, more than one antenna, because we can constructively recombine different parts of our waves, of our electromagnetic waves of the signal, which means more energy we receive. Because in the end, all we do is we emit some energy from the antenna into space, transmit the energy and try to receive it. Yes, this is only some picowatts, femtowatts, whatever our antennas receive. Yes, but that's enough. Okay, and now we can directly go to something that is quite new. We can use this. And that's exactly what you find under the term of MIMO. MIMO means multiple input, multiple output. So MIMO technology is the core technology when it comes to antennas for today's communication systems. So no modern communication system uses only one antenna anymore. We all use several antennas. So MIMO means multiple input, multiple output. That means we use several antennas for receiving signals and for transmitting signals. So at receiver and transmitter, several antennas. So this is why we have higher data rates. This is why we have longer transmission ranges, etc. We have higher bandwidth, etc. Higher what we call spectral efficiency. Spectral efficiency means how many, in the end, what we're interested is bit per second per hertz. So per fraction of the spectrum, how many bits per second can we transmit? We're interested in bit per second. So fading, I will come back to what does it mean, this fading. So examples, that's exactly what you use. 802.11n, that's one of the wireless LAN standards. LTE. LTE is the core technology for the current mobile phone generation. The 4G, almost 4G. It's not really 4G, although advertisement is always for 4G, but it's 3.9 or 4G system. HSPA plus is UMTS with higher data rates. So this is exactly what today's mobile phone can handle. The interesting thing is you can not only receive signals using different antennas, but you can also transmit signals using different antennas. What does it mean? An antenna can always receive and transmit. That doesn't matter from physics. So if you have a certain quality for receiving, it's the same quality for transmitting data. So you can also use your cell antennas for transmitting something. So that's interesting. So you can use, in our case, 3 antennas. They all emit the same signal, but with a slightly different phase. In a way that the signal can be composed in a constructive way at certain points in space. So the antenna that is a little bit further away first starts with transmitting the signal, then the antenna 2 in our case, then antenna 1, and then all those signals come together at certain points. And this is called beam forming. So actually, with these antennas, you're using the devices, you can follow another device. You can follow a certain user. This means you can form your beam to a certain point. And this now allows for spatial multiplexing. If you think of a marketplace with 100 users, you can form 100 beams in an electronic way, and you can directly follow those users. And the big advantage is, if you form the beams, you minimize interference with respect to the other beams. You can directly follow something. This technology is used for military purpose to follow single aircrafts, for example, and it's difficult for the enemy to receive anything, because if you're outside this point, sure, the waves continue somehow, but they all have a different phase, and if you compose them, and if you do not know the signals, they will cancel out each other. You will not really have a good reception of the signal. So that's the idea. So you can basically form the beam, and how you then actually do this so that they do not interfere, etc. There's something called diversity coding, using certain so-called orthogonal codes. I will introduce this in the next chapter. What this means, you can do spatial multiplexing, you can split high rate signals into several low rate streams. You can do many interesting things, but the most fancy one is really this beam forming, where you can actually follow single persons or single devices. And this further increases the spectral efficiency. Why? Because you can use exactly the same frequency range at the same time by multiplexing in space. So you have different beams and they do not interfere, because you focus one of the beams for this user, one of the beams for that user. And this is all handled in an electronic way, so you do not actually have to move someone with your antenna. That has been done many years ago. Maybe you saw some of these old applications, or military applications, where you had to follow with your antenna, and today you do this in an electronic way. So you can actually move your beam in an electronic way by changing the phase, by delaying more or less your signal. This is how you form your beam. So that is used, and that's more or less the most enhanced way of using your MIMO technology. You can also use MIMO, for example, that you say, okay, for my TV set, I assign this and that antennas, and for the mobile phone at home over wireless LAN, you assign another antenna, things like this. You can also do this kind of multiplexing, but beamforming is very fancy. So you can have good utilization of your space. Because otherwise, without beamforming, you have a problem. You can imagine you use the same frequency for all the users. Somehow you have to separate them. We will learn how we separate, but space division multiplexing is one technology. So quite interesting, this beamforming thing. Okay, that's what we can do with more than one antenna. And that's, if you're interested in this, just look up the standards. There you can find how beamforming is used there. Beamforming, be aware, with a normal mobile phone, you cannot do whatever you want with respect to beamforming, because this also needs a lot of computational power to create the signals, etc., etc. So that's not that simple. Computation power also is reflected then in power consumption. Okay, now we know at least a little bit about antennas. Okay, so we have antennas, we know what signals are. Now we start transmitting the signals. I showed you a signal, well, just as a red line from sender to receiver. Yes, reality is a little bit different. When a signal travels through space, the signal gets weaker and weaker and weaker. Why? Very simple. Think back, we have this ideal isotropic radiator, theoretical construct. And we say a wavefront is like a balloon. The balloon has a certain thickness of the rubber is made of. So if you pump air into the balloon, it becomes larger, 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 but the material thinner and thinner and thinner. And similar, you can think of your wavefront. You put a certain amount of energy into this wave, you emit it from the antenna. There's a certain amount of energy in this very single point, and then you distribute the energy over the surface of this sphere, and the sphere gets larger and larger and larger. So in the end, if you measure the energy at a certain point, the surface of the sphere, you measure less and less energy depending on the distance to the point where you emitted the signal. And as the signal gets weaker and weaker and weaker, well, you sooner or later come into the problem that you cannot receive anything anymore. And we distinguish between a so-called transmission range. Transmission range, that's this dark gray circle around the center. That means you have enough energy to communicate. That means the error rate is low enough, the bit error rate. So if you have your mobile phone somewhere here, it's very easy to communicate. Then we have a certain detection range. Detection range means we at least detect, oh, there's a signal, there is something going on. We cannot communicate too far away, but we know that at least there's a sender. Okay, detection range. Why this is important we will see when we come to medium access mechanism. And then we have an interference range where we do not even detect that there's a signal, but the signal adds to the background noise. So if you're further away from an antenna, you cannot say, oh, this is a wireless LAN, or this is GSM, or this is this or that. You just experience noise, background noise. And the problem now is always we have to keep an eye on the so-called signal-to-noise ratio. Remember, there was Shannon limit, etc., where we said, okay, the signal-to-noise ratio basically limits our data rate. And if we have too much noise, we have a problem. Okay, so now this again is an idealistic picture, because the problem is that in real life, we do not live in vacuum. We have obstacles, whatever, so transmission ranges might look like this. And also detection ranges might look like whatever. And interference range, who knows? And that's one of the problems. So it's more this kind of bizarre shade figure. And then we also have the problem it's time varying. So this might be true in this second, and the next second it looks completely different because a huge truck is crossing the road. And then suddenly your signal breaks down because it's blocked by the truck. So, or you drive your car and then you experience many problems with the signals because this picture changes. So signal propagation might be simple in vacuum, in theory, but in real life it's way more complicated. So it's not a simple formula you can use. There are formulas, yes, but they all assume certain characteristics of the environment, like open space, like rainforest, like an urban environment. But as soon as something changes, the weather conditions or road traffic or whatever, this picture changes pretty much. So what happens in real life? So this was all vacuum. In real life, many things happen to your signal. Free space, your signal travels straight ahead, like a straight line. We ignore gravitation for now. You might know that gravitation bends your signals, but that's something different. So we ignore it by now. For us here, we assume our wave states simply travel a straight line in space. The received power is proportional, well, to 1 divided by the squared distance in vacuum. Why? Think back to our balloon, the sphere. We emit this amount of energy from our idealistic point. Now the sphere grows and grows and grows and grows. And basically your energy is the thickness of your balloon. You can at least think of this. So you receive less and less and less energy. In real environments like we have here, it's more like d to the power of 3.5, 4, something like this. So now, if you think of all the discussions around the danger of base stations. A base station emits, let's say, 10 to 40 watts. So now you emit this certain amount of energy, so watt per second. You emit this, but the energy you receive here with your human body, if you are 100 meters away, 10 meters away, whatever, depends on the distance, the power of 3, 4, depending on obstacles, buildings, etc. So what you receive here is in the range of femtowatts, picowatts. Well, difficult to measure. You can measure it because you can receive it. But now compared to 1 watt, quarter watt, close by your brain with your mobile phone. These are factors of more than 1 million stronger, the energy, the signals, compared to the signals you receive from base stations. So if you believe in the danger of the radiation, then you should never ever use any of these devices, the wireless devices close by you, but you should not be afraid of a base station somewhere on the roof. Yes, it's visible. Maybe it's not really nice if you see the base station. But when it comes to the radiated power and the energy you receive with your body, that's really a small fraction of the energy you receive by simply placing a mobile phone close to your ear or Bluetooth headset or whatever. So, okay, also when it comes to the energy of you heating up your brain, yes, you do. Sure, you heat up your brain with electromagnetic waves. Yes, that's the idea of a microwave oven. But compared to the sun, that's almost nothing. You can measure it. Sure, you can measure it because the brain consists of water, absorbs energy, etc. Yes, you can measure it. But compared to the sun shining on your head, that's almost nothing. So it's always interesting to see the relation and remember of this receiving power proportional to 1 divided by d squared in vacuum, in real environment, d to the power of 4. And then you see, okay, that's really not even 1/1,000,000th of the signal strength you have with your mobile phone close by your head. Okay. And then in real life, real environments, you have many more effects like shadowing of signals. If you have a wall, if effect called shadowing, well, yes, that's what you know as shadow from visible light. The same happens to electromagnetic waves, depending on the material. You have effects like reflection. This, by the way, is the reason why we can use our mobile phone almost everywhere, because we have reflection. It's very, very seldom that you have a direct line of sight to a base station. But you can use your mobile phone inside the room, inside buildings, on the road. Why? We have a lot of reflection all over the place, reflection of our electromagnetic signals. Now think of the time traveling for the signal, the so-called time of flight. What happens if you have a lot of reflection? We'll come back to this. We have effects like refraction. That's what you know from visible light if you look into water. So the object is not at the position where you think it is. If you look at the fish, for example, and if you want to catch the fish is not where you think it is. When you look into the water, we have refraction. The fish is much closer to you, for example. You have scattering, diffraction. These are the effects you learned in physics at high school with the laser, and you had this small gap, and you see then these nice patterns, scattering, diffraction effects, etc. So that's exactly the effects you have with all electromagnetic waves. Might it be light or the waves, the lower frequencies we use here for radio communication. Okay, many different effects. Okay, why do we talk about these effects? Because it really influences the behavior of all wireless communication systems. If you look now at real-world examples, on the left-hand side we see one floor of a building, and there we have a wireless LAN hotspot. Those pictures, by the way, you can generate by ray tracing. Ray tracing, the same technology you use for generating images, computer images. So ray tracing you can use, okay, here as well, if it's light or other electromagnetic waves, doesn't matter. You just need the characteristics of the material. You have your hotspot somewhere, and you see, really nice, here, the attenuation of the signals. So the signals are weaker in one of the rooms, are stronger in other rooms. You see the reflection at the walls. These are exactly the technologies used for placing base stations or hotspots or these wireless LAN transceivers. So you go through the building and you measure the signal quality. You can create these maps beforehand that they're not 100% accurate, but you can create them. Then you can think, okay, maybe it's a good idea to have another access point up there, because depending on the signal quality, your data rate is higher or lower. So you see what happens there. Or here, that's an example of Munich downtown. We see what happens if you have higher buildings. Like, oops, you don't see this. Here you have higher buildings. Suddenly you see the shadow of these buildings. You have a base station, a GSM base station, and suddenly you have the shadow of this base station. That means maybe you need another base station here because of this shadow to have better coverage of a city. Or on the right hand side, you see here, this is the Rhine Valley here, and the Black Forest on the left hand side, France on the right hand side, and you see what happens. This is a radio station, Honnesgrinde, transmitting the electromagnetic waves down into where people live in the Rhine, along the Rhine River. But you see what happens. These are the shadows. If you live in one of these shadows, you have very poor reception with your, in this case, maybe classic analog FM radio. Different frequencies. You see also up there in the sky, very good reception for an aircraft. So, okay, that's exactly the same that happens when the sun shines somewhere, you see shadows, etc. So that's quite interesting, real-world examples here. So, and this happens, and it depends also again on the wavelength. So in physics, you use a laser, visible light, and a very, very, very fine, tiny gap. Or if you have a crystal, you use X-rays to see the crystal, the interior structure of the crystal. Here we have much lower frequencies. So the effects we see here, they already occur at larger objects. So we don't need a crystal. We can use the Black Forest or a city or whatever. So you see, in real life, this is why I always say wireless communication is not the same as using a wire. You see, these effects, they make planning way more complicated compared to a wire. If you have a wire, fiber, it's simple, you know, oh, this is where the wire goes, this is where my data flows. Simple. Here, with wireless, it depends. And what makes it even more interesting, this is not static. You might think, oh, the buildings are static. Yes, maybe the buildings are static, but we will learn more about technologies like UMTS, where the size of such a communication range very much depends on the load you have in the cell. So how many bits per second others transmit. So those cells may shrink, for example, which makes it much more complicated to actually calculate in advance where can I place my base stations. So it's a little bit more complicated compared to the classical technologies. And so for a building like here, we have, I don't know, 20 something base stations. These hotspots for the whole campus, 1,800 and something. Why? Because full coverage with higher data rates requires more antennas. And one thing you can remember is, if you really want to have higher data rates and good coverage, we need more and more antennas. We cannot have one single antenna with a high output power. It doesn't work. So we need more and more antennas. And by the way, we need less energy if we have more antennas. It sounds strange, but it's true. Because of this d squared or d to the power of 4 rule, we need a huge amount of energy if we have only few antennas compared to having many smaller antennas. Because it's not a linear relation, but it's this d to the power of, depending on the environment. So this is just to give you some impressions how it looks in real world. Okay. And now to make things even worse, there's something we'll discuss from time to time throughout the whole lecture, and it's called multipath propagation. Up to now, I talked about a line of sight. So a sender sends something with antenna to receiver. Sounds simple. But now we learned, in real life, we might have effects like reflection, scattering, whatever. And now only looking at 3 different paths of our signal, we see they will be received at different time here at the antenna of the car. And these are only 3 possible paths. Please remember that in real life we have an arbitrary, infinite number of paths. Because, there are many reflections on tiny sand grains or on whatever, leaves of a tree. We have scattering and all these nice effects. The question is if they are interesting or not, if they really contribute. Here I show only 3. What happens? We learned that it takes some time for the signal to travel from the sender to the receiver. So what happens if we only look at one of the signals? The first one here. So we send out this peak, just for example. What we receive is first of all the so-called line of sight pulse. Line of sight is always the shortest connection. There's always a line of sight. If there's a line of sight, that's the shortest connection. Okay, so that's the first pulse we receive. And then we receive, in this example, 2 more multipath pulses. So, that's due to the multipath. In real life, again, we have many of these paths. So what happens is we have this nicely shaped signal at the sender, and at the receiver, we have some kind of this smeared out, not really nice signal. And hopefully we can still receive something. What happens then if we have a second signal? Nicely separated. At the center, we see there's a nice gap between the first signal and the second one. first symbol, a second symbol. So first we send a certain point in our constellation diagram, and then we send another one, whatever. So it's clearly separated. What happens now on the receiver side, we see that from the second signal, the line of sight pulses, that's the second one, O, suddenly overlaps with one of the multipath pulses from the first signal. So although we clearly separate the signals on the center side, they overlap on the receiver side. That's not nice, because they might cancel out each other. And it's not always the case that the multipath signals are weaker compared to the line of sight. Just think of, you have a concrete wall directly in the line of sight. So between you and the other antenna, there's a wall. So the direct line of sight exists for the radio waves, but the concrete wall weakens the signal. And then there's a reflection. Reflection takes more time, but the signal might be stronger. So that's just an example. So the multipath pulses might be stronger than the line of sight pulses. Just be aware. If you have, for example, a concrete wall directly in the line of sight. So it might easily happen that with a multipath pulse, you cancel out other multipath pulses, although the original signal had been clearly separated. See, what you experience is interference with neighboring symbols. Symbols, we come back to this term. So you send something, then you send something else, and suddenly they overlap, they interfere. And that's called ISI, intersymbol interference. So, that's a problem. What is the solution? Basically, you have to separate the original symbols even more. But if you separate symbols in time, data rate goes down. So multipath propagation, in the end, limits your data rate. If you experience more and more of this ISI, this intersymbol interference, you have to lower your data rate. That's exactly what all mobile communication systems do. They lower the data rate if they experience more interference. They change the modulation, as we will see, but they lower then the symbol rate, because they know, okay, we have now a problem over there. So you can lower the symbol rate. That's one of the solutions. There are many other solutions, but that's one thing you could do to widen the gap between the symbols to lower intersymbol interference. But that means lower data rate. So multipath propagation is a problem. Now just consider you walk down a road and, well, you don't see the base station, and you can imagine how many of these multipaths you have. Yes, it's an infinite number, but so many different ways of reflection, and there's some refraction, multiple reflections, so it can be a kind of a zigzag pattern, some multiple reflection between buildings, etc., etc. And the more reflection you have, the longer the path is, and the more the phase shift is. And somehow your antenna has to handle this. And we will see, for example, there are receiver types that always go to the strongest signal, no matter what the delay is, and we pick out only one of the signals, so the strongest path. There are other receiver types that always pick out the 5 strongest signals, and they always check if there's a stronger signal coming from somewhere and then replacing one of the 5, and then recombining these signals all the time. But this requires many additional mechanisms, a lot of power control and things like that. We'll come back when we talk about third generation systems. So multipath propagation, another effect. Yes, now you're mobile. So this is already stationary, not mobile. You have multipath. Now in addition, you're mobile. What happens? Well, you move. So you have all time different multipaths. You remember, you have infinite number of these paths, and now they change over time. So the signal paths change, you have different delays, delay variation, different phases, etc. And it might happen that you have quick changes in the power. Imagine a car driving down an alley with a lot of trees. So the signal breaks down all the time when you come by a tree, for example. So short-term fading. In addition, you might move away from the base station. So the average power decreases or increases. That's called long-term fading. So a slow change in the average power received is long-term fading. What can we do against it? If you have short-term fading, well, you cannot know in advance that this happens. It's not slow, so it's very fast, changes. So maybe suddenly your signal breaks down and it's back again. Could you imagine how can you now, if you think in bits you send, how can you actually bridge this problem? So maybe you lose here part of your data. What can you do? You lose part of the data, forward error correction. Something I also introduced in telematics, forward error correction. So all the wireless systems use heavily forward error correction. So for example, the classical GSM system has a data rate over the air of, let's say, 22 kilobit per second. But what you can use is only roughly 10 kilobit per second. Why? You use a lot of forward error correction. So you insert a lot of redundant data. Because in case of this short-term fading, what can you do? You lose some bits. So use forward error correction and you recalculate the missing bits. And for long-term fading, that means, the received power goes down, etc. What you do there is actually you have tight power control. So the further away you are from a base station, you can transmit with more output power. If you're closer by the base station, you can lower the output power again to save energy, because more output power means you drain the battery faster. So you can adapt. That's exactly what the mobile phones do. So the classical mobile phones, something like 50 to 100 times per second. Third generation systems, 1,500 times per second, they adapt the output power, 1,500 times per second, to reach more or less the optimum output power. And for these for these very short interruptions of the signal, well, you could, for example, use forward error correction to bridge this gap. Long-term fading is more handled by a power control. Okay, so these are some of the effects if you're mobile. Remember, multipath propagation happens even if you're absolutely stationary, but then it's easy for the system to adapt. But if you're then in addition mobile, it's not that easy to handle. And you should keep this in mind if you get angry about the low quality of the wireless systems. Remember, they have to do a lot while you travel at 200 kilometers an hour in a train from A to B or 250 or whatever, and they have to adapt all the time, transmit power, reflection, etc., etc. So it's a little bit more complicated. So now that's more or less enough about all these problems of wireless transmission. So we know antennas, roughly what's going on in antennas. We know the problems of signal propagation, what happens to the signal, and now we have to transmit. And you know that we all use the same space of antenna to send, to receive, and we all use the same space. If we use our laptops here, our tablets, we all use the same space at the same time. More or less the same frequencies, maybe. And we already learned in telematics that we can use multiplexing to separate different channels or users. And one way of separating users is space. We can use several cables. That's space division multiplexing. For wireless systems, that's the classical way of separating users is place them further apart, like a radio FM station in Stuttgart, one in Berlin, one in Hamburg. They can all use the same frequency. There's almost no interference, no problem. So, but we need something, it's called the guard space in between. So we have guard spaces. Or the beamforming, it's just explained to you. So that's also space division multiplexing. So space division multiplexing helps to distribute different channels or different senders in space. That's nice, and with beamforming we can even use it very close by. But that's not the only tool we have when it comes to multiplexing. You know from telematics also time and frequency division multiplexing. No big surprise, we can separate the channels in frequencies. That's a classical thing we do in wireless. Well, for classical FM stations, we have one radio station at 104.6, we have one at 92.3, we have one, etc., etc. They have guard spaces in between. Very simple. Works also for analog signals. And it's okay if you have this typical 24/7 operation. So you operate a radio station, FM station, the whole day. But it's a waste of bandwidth if the traffic is distributed unevenly. So that's exactly what we have for mobile phones or for wireless LANs. You do not transmit 24 hours the whole week. So use it only for short bursts. So if you have your own frequency, that's a waste of the spectrum. And spectrum is a scarce resource. So it's not very flexible. It's simple, it's okay for TV stations, okay for radio stations, but what happens if you don't have to send anything? Not a good idea. So this is why in all our also classical fixed systems with wires we also use time multiplexing. So you get the whole channel only for a certain amount of time, so the whole frequency range. So time multiplexing, but there, this is exactly what we do on all normal LAN systems, etc. But we need precise synchronization. That's a little bit more difficult in wireless systems, as we will see. Time multiplexing. No big surprise, time and frequency multiplexing. And then we can combine both. Yes, time and frequency division multiplexing, that's exactly what we use, for example, for a Bluetooth system. We will learn that Bluetooth jumps through different channels all the time. So at a certain point in time, it uses a certain channel. And then 625 microseconds later, it uses a different channel and jumps and jumps and jumps and jumps all the time. So it does frequency multiplexing, also time multiplexing. The same can be done for GSM, so you can use different channels at different time. So that's quite nice. For example, if you have frequency selective interference, so you have a lot of noise on this frequency, so basically you destroy all the signals on this frequency. Well, yes, if you're one of this pink sender-receiver pair, you still have these other pink blocks, for example. And we will also learn that if we assign at a certain time more than one of these channels, we can achieve higher data rates. And that, by the way, is exactly the basis for LTE, the fourth generation of mobile communication systems. They do a very elaborated time and frequency multiplexing. So you use at a certain time certain frequencies, and you can even use more of the spectrum at the same time, etc., etc. So we'll come back to this. So up to here, this is more or less, these are the classical multiplexing technologies: space, time, and frequency. Okay, so that's for the basics. And then the next time, Okay, so good morning everybody and welcome back to mobile communications. The last time I introduced the basic multiplexing technologies: space division multiplexing, frequency, time division multiplexing. And the last slide I showed you last week basically showed you how you can combine time division multiplexing, frequency division multiplexing by allocating a certain fraction of the spectrum for a certain fraction of time to a sender and receiver pair. So over time, more and more different systems have been developed: mobile communication system, analog TV, etc., etc. And the problem over the years was that, okay, as soon as you had a new technology, the new technology typically was more efficient. So you could transmit more bits per second per hertz, per fraction of the spectrum. But what happened, for example, here in Germany, we still had the analog TV. So how can you use this spectrum? Well, you can actually say, okay, 2 years from now, we stop all analog TV and we replace this technology by a new technology. That's one way of doing it. Okay. Another way of doing this is, okay, let's have some kind of a smooth transition. And this is where you can use the so-called cognitive radios. What does it mean, a cognitive radio? Basically, and that's the typical cognitive radio, a spectrum sensing cognitive radio. It's a radio that tries to receive something and tries to detect unused spectrum. So that's the idea. So you try to detect unused spectrum and then share it. So that means you scan the spectrum, and as soon as you detect, okay, no one is using analog TV, the spectrum for analog TV here anymore, then I can use it for whatever other technology. So that is one way, and you can then automatically choose the best available spectrum. Something similar is done today with wireless LAN systems. So you scan the spectrum, you scan all the available channels, and then your DSL router usually decides, okay, well, there are maybe 10 wireless LANs on channel 1, but there's only one on channel 4. Then I go on channel 4, something like this. So, and together with this cognitive radio, you can establish a system that looks as follows, that you have radio antennas and so-called primary users. A primary user is the one that is, for example, by regulation assigned to a certain spectrum. So this is the user that pays for the spectrum. And there might be secondary users. They can use the spectrum if there is no primary user. So that is one idea. So what you can do is, you can say, okay, for example, you have an antenna here, and now depending on, maybe there's still a deployment for classical, now let's stay with analog TV here in this region, because there's still an analog TV station. Then you have primary users and you have someone who paid for the spectrum. Then it's not allowed to use the spectrum in this region for some other secondary users. But there might be regions where there's no analog TV anymore, or there has never been any analog TV, think of desert or whatever. Then you can reuse, if you need it somewhere in the desert, you can reuse the spectrum there. So you can reuse, for example, unused analog TV spectrum, so-called white space. Or you can also do it like if you have a kind of a temporary reuse of unused spectrum. So quite often we have spectrum allocated to a certain technology, but it's used only 1% of the time. Then you can reuse it the other 99% of the time. And if you do this in a very flexible way, then we end up in a scenario as shown here, where you have kind of very flexible way of multiplexing primary users, secondary users over time, using more or less of the spectrum. Here the spectrum, you see the frequencies on the y-axis. So you allocate a certain amount of the spectrum to a primary user. If there's no primary user, then a secondary user can use it. But you have to scan the spectrum all the time. As soon as there's again a primary user, you have to stay back, and the primary user can use the spectrum. If the primary user stops, you can recognize this, cognitive radio recognize this, oh, then I can use the spectrum. That's just an example. So cognitive radios, that's one technology you should have heard of that basically can reuse unused spectrum. And even if this is only for some milliseconds, so if there's a gap somewhere in between, you can jump into this, but you must not interfere with the primary users because they pay for the spectrum. So that's one of the ideas. So here in Germany, quite often it's done by regulation that they say, okay, we had analog TV until, I don't know, 3, 4, 5 years ago. That has been replaced by digital TV. Now the digital TV on certain frequencies is replaced by a new digital TV technology and by LTE, etc., etc. So cognitive radio, that's one of the terms that's quite interesting, that you can jump on certain frequencies for a certain time, but you have to sense the spectrum all the time. You can sense it and see, okay, if it's unused, then you can jump into this. So that's one of the newer technologies because it requires some computational power. Okay, so this was all time and frequency multiplexing. So there's now, with wireless communication, one a little bit more strange technology, code multiplexing. I will explain this, how it works, later on when I come to the multiple access technologies, because then you will learn how you create a certain code that allows the code multiplexing. So code multiplexing basically means that all the users use the same frequency at the same time. But you can distinguish the users by a certain code. And now the trick is how you actually generate the code. They will learn it's a kind of so-called orthogonal codes, how you can you code your data and that you can calculate certain bit sequences and recalculate your original data, etc. We'll look into this at least a little bit. So, but the idea here is that we have, in addition to space, time, and frequency, this fourth method of code multiplexing, where you say, okay, you assign a certain code. And the big advantage here is you don't need any special coordination. So in the end, what you do is you just assign a certain code, and then whoever wants to communicate uses the code, and if you know the code, you can communicate. If you do not know the code, all the data sounds like noise. You cannot receive it. And I will explain how this works in the next chapter. So the big advantage is you don't really have to coordinate this. Well, there's some coordination, but not coordination like in time multiplexing. I say, okay, this is the time slot, and every 1 microsecond you switch from this time slot to that time slot, or whatever. Or like in GSM, where you repeat a certain time frame every 4.165 milliseconds. You don't need this here. And there's a big advantage, as we will see. It's a good protection against tapping. So if you do not know the code, the special code, it's talking in a foreign language. If you don't know the code, if you don't know the language, you do not receive anything. This sounds like noise. You will not understand anything. So that's the idea. Disadvantages, we also will come to disadvantages. The data rates available, and this happens, for example, explicitly for UMTS, the third generation technology, they vary depending on the other users, depending on the noise, as we will learn. And it's a little bit more complex to regenerate the signals. It's not that simple. We will also learn a little bit more about this. And also how we implement this and what this has to do with so-called spread spectrum technology. For now, it's enough for you to know, okay, besides space, time, and frequency, there's a fourth method for multiplexing. So that senders and receivers use the same frequency at the same time. And the how will be explained in the next chapter. Because this is tightly coupled with medium access, coding, and also, if you want, encryption. If you do not tell anyone the code, how you code it, well, then no one can listen to the conversation. But first of all, we have to learn, it says implemented using spread spectrum. What does it mean? What is spread spectrum and why do we use it? So for now, basically, we looked at channels, what we call narrowband channels. These are all channels on certain frequencies. And there we modulate our data on the channels. Okay, so modulation technologies, and then we have channels. But there's also a technology that says, no, I don't want to use a narrow channel, but I use a very wide channel. Why this? I will explain it after we learn more about modulation, because this is what we need for all this spreading and all this thing. So for now, we have the channels, we have our digital data, okay, but we have to translate it. And there are two steps. One step is we have to translate the digital data into an analog signal, a so-called baseband signal. And we also already learned in telematics what you can do. analog frequency, amplitude, frequency, and phase shift keying. That means you influence the amplitude, the frequency, or the phase of a signal, depending on the bits. Okay, and there are many different differences in efficiency, robustness, etc. That's the main focus here. And after you have your so-called baseband signal, I will give you examples, then we have to shift the signal onto a radio carrier. That's the next step. So first, usually, well, we generate our baseband signal and then we shift it onto a carrier. Why? Well, think of radio stations. Radio stations, someone speaks, you have music, and they all generate a baseband signal roughly in the same frequency ranges. So we have speakers for news, etc., and they all generate more or less baseband signals, same frequencies. But then you allocate a certain carrier frequency, like 94.3 megahertz to one radio station, 104.6 to the other one. So you have to shift this baseband signal onto the carrier to enable frequency division multiplexing, for example. And we also learned that the antenna size depends on the wavelength. So transmitting a baseband signal requires huge antennas. So this is why we shift it to higher frequencies. And we have this lambda half, lambda fourth, depending on the type of antenna. So we can have much smaller antennas. Frequency division multiplexing plus medium characteristics. I told you last time that you cannot simply penetrate a wall or whatever with arbitrary frequencies. Light, for example, does not penetrate a concrete wall. Radio waves, low frequencies, they can easily penetrate the walls. Or if you have very long, low frequencies, long waves, they have different characteristics, etc., etc. And there are also three basic schemes how you can do this analog modulation: amplitude, frequency, and phase modulation. So you have the shift keying technologies. They translate basically the digital, the data, into an analog signal. And you have then the analog baseband signal you can modulate on a carrier frequency. These are the classical two steps you can do. In real systems, you have several intermediate steps. Not interesting here. Okay, so what do we do? Very simple. Here we have our digital data. Digital data coming in, our ones and zeros. Then we do this digital modulation. So our shift keying technologies, amplitude, phase, frequency. Then we have our baseband signal. Then we use a carrier. So this is now for a radio station, for example, the 94.3. And then we do, for example, frequency modulation, FM, for this radio station. And then we transmit it over the air, we receive it, we do demodulation, we have an analog baseband signal, and then we have to actually decide what this fraction of our waves, what they mean. So that's the decision here. We have somehow to synchronize and see, okay, this is where the bit starts, and now this fraction of our wave means a 0 or a 1. And then we recreate the digital data. That's the basic idea. Okay, modulation, demodulation. Very simple. And how we do this? Well, these are our three digital modulation schemes, also known as shift keying. So we can, for example, and this is a very simple scheme, simply say, okay, we use a sine wave to represent a logical 1 and nothing to represent a 0. So amplitude shift keying. And that's already enough, for example, for laser and fiber optics, light on, light off. Very simple, very simple. We can also say, okay, that's very simple, but you can imagine if we have interference, not in fiber optics, but for our radio waves, there could be some interference here. So what is this now? A 0? Or is this a 1? We don't have something like 0.75 or whatever. These are logical values, so 0 or 1. So how? We don't know. So we have to decide, then we say, okay, this could be a 1, and this is how we create a bit error. That's all. And then we have all our tools like forward error correction, automatic repeat request, from telematics, to correct the bit errors. But Here, in this stage, we don't know. We have to decide on the receiver side. Frequency shift keying, basically, you use one frequency here, one frequency F1 for 1, and one other frequency F0, for example, for the 0, and then you basically change the frequency. Higher frequency, lower frequency, higher frequency, for example. So you code your bits into the frequencies. That's, by the way, what you hear in a classical analog acoustic way for the old fax devices, when they start sending their different tones over the classical analog telephone line. And then we have the most robust way of digital modulation. You code your data into phase change. Here you have a phase change basically of pi or 180 degrees. So you code the change from a logical 1 to a logical 0 into this phase change here of pi, and again here. So that's also, it's a little bit more complex, it's very robust, because even if you have noise, the noise will change this nice sine wave, but you will still be able to detect the phase shift. That's the idea. The problem there is that nature doesn't really like these phase shifts. Because if you transmit such a signal, you automatically generate, because this is nothing nature can do, this 180 degrees, you generate very high frequencies, a lot of distortion, etc. So we'll see a scheme used in GSM to avoid this. But these are the three basic schemes for digital modulation. Exactly the same we had for modern technology in telematics. So nothing new here. Okay, digital modulation. And then over time, over the last 20, 30, 40 years, we've developed more and more elaborated schemes, more advanced, for example, frequency shift keying schemes. And one used, and this is, I will explain in a figure, is the so-called Gaussian minimum shift keying used in the classical so-called second generation mobile phone system GSM. So that's the classical, just to give you one example. I will not go through all the examples, so you can read. Just to give you the example, what is done here. So minimum shift key, you have your data, your incoming data 1, 0, 1, 1, 0, 1, 0, and you split this into even bits and odd bits. So you basically, well, that's the idea. You double the even bits. So that's the even bits, for example, you double, and you double the odd bits. So that's the first bit here, the first, the second, the third bit, the fourth bit, etc. And you double them. And now there's a simple rule. You check the even and the odd bit. So the even bit is 0 and the odd bit is 1. The even bit is 0, the odd bit is 1. Okay, and then you go into a table, and then you decide the frequency and the phase shift of the signal. So that means, okay, for 0 and 1, you go for the lower frequency. So that's here. That's the lower frequency here. And it says original signal. So that means the resulting signal is this. Why is this done? Now, if you look, the resulting signal, no matter what the input data is, you will never have a phase shift in here. But you have lower frequency, then you go to higher frequency, lower frequency, and all you have is this, well, this change from lower to higher. And this avoids, for example, this the distortion, so this minimum shift keying. So you have no abrupt changes in the phase, but you switch from lower to higher frequencies. If you just switch between arbitrary two frequencies, there might be extreme phase shifts in between. You jump in your signal. Nature doesn't like this jumping into the signal. It doesn't work. So you create these high frequencies, etc., etc. But here you can avoid this. So the signal, resulting signal, looks smoother. And this is then the resulting signal. You then modulate onto a carrier and then emit over the antenna of your mobile phone. Basically, that's the idea. And the frequency you choose, well, that depends on basically, well, network operator, the channel that is assigned to your mobile phone, etc. So that is one of the ideas how you create such an MSK signal. And that's just one example. But to go into more examples, that's again electrical engineering, just to show you what is done there. And there are more and more examples. I also showed you already when we talked about modem technology. Now we are back in the constellation diagrams. So a very simple scheme, binary phase shift keying, where we have a 0 and a 1, or a little bit more elaborated, the quadrilateral phase shift keying, where we can code 2 bits per point in the constellation diagram. Why? Well, it's nice to code 2 bits because then we double the data rate, but if we have interference, the receiver might receive something here, maybe here, and then can decide, okay, this is still 0, 1. But if we have a lot of interference, it might happen that this original point is shifted somewhere here, and suddenly we say, oh, no, this is a 1, 1 and not a 0, 1. So we receive bits with errors. So if you have only 2 points in the constellation diagram, the 0 and the 1, then no matter what you receive on this right-hand side, it will always be mapped onto the 0, and on the left-hand side, always mapped onto the 1. So it's more robust, but lower data rate. So that's one of the ideas. So QPSK, you code 2 bits in one symbol. It's a little bit more complex and not as robust, but you have double the data rate. So depending on the noise level, depending on the interference, you can code more or less points in this constellation diagram. That's the idea. So, and then there are many similar schemes that you do code relative phase shifts or relative to the preceding bits, so differential QPSK, etc., etc. So these are classical second generation mobile phone systems. And we can continue this just to show, yes, we can even code more and more bits. So that's what classical modem technology also used. So we code 4 bits per point in our constellation diagram, as you see here. And now we have different amplitudes. That's the radius of the circle. That's the amplitude of our signal. And different phase shift depending on what bit combination we transmit. That's the classical quadrature amplitude modulation, or QAM. And this can now be, as you can imagine, we can do more and more and more. And that's just one example we use for the classical television, the digital television. So DVB-T, and they do something very tricky. They say, okay, we transmit high priority data and low priority data. So we transmit per point in the constellation diagram 6 bits. 6 bits, very simple. Okay, 6 bits. So if we have almost no interference, so we receive something around this point or something around this point, it's for us, it's easy to reconstruct the original data. If we experience more and more bit errors, that means more interference, then we hope that maybe this point is mapped somewhere here. At least we can decide, are we in the upper right-hand corner, lower right-hand, upper left-hand, lower left-hand. So that means at least we can decide what are those 2 bits, those higher order bits, and they have a higher priority. So in case of interference, we at least we know what those 2 bits are, the high priority bits. We don't know what those low priority 4 bits are, but we know it's somewhere in here. And now we code the more important parts of the picture in the high priority bit and the less important part in the lower priority. For example, you have, depending on the codec you use for MPEG, you have iframes and BNP and whatever, different priorities of frames where you transmit the whole frame and then only differences. So maybe in higher priority you transmit the whole frame and then the delta, the difference with low priority, then parts of the picture they freeze. but at least you receive something. For example, you can switch off color or whatever. So with good reception, you can resolve the entire constellation. Poor reception, at least it's something like QPSK. So that's one of the tricks. For the system currently being introduced, DVB-T2 uses a newer modulation scheme and uses also a new codec, H265, with a special configuration to transmit high definition video. So HD video, currently DVB-T has no high definition video. So HD is possible with the new DVB-T2, which means new receivers for all classical TV using this digital terrestrial video broadcasting. Okay, so that's one way of doing this modulation in a kind of a hierarchic way. That's quite nice. And just be aware, just remark, if you buy DVB-T2 devices, please check if they are really for the German market, because we use a different codec compared to Austria or the UK or whatever, because they cannot transmit these H265 high definition videos. But they are also called DVB-T2. So take care that it's really the one for the German market. Okay, and I think from next year on, mid next year, there will be no classical DVB-T anymore, only T2. So now we know, okay, we can do a lot about this modulation. And now this is state of the art, I would say 20, 30 years ago. But there's more you can do. One problem is in all radio transmission that you have interference. That's different from your cable, interference. And there's one really mean type of interference, if it's a narrowband interference exactly cancelling out your channel. So if you have 20 channels and you use channel 13 and the interference exactly cancels out channel 13. That's not nice. So we have sometimes narrowband interference. What you can do is basically, instead of transmitting your signal using a narrow band, you spread out your signal over a larger spectrum. Okay, so instead of putting all your energy in this narrowband signal, you can actually spread out your energy over a larger spectrum. So instead of using a channel of, let's say, 20 kilohertz, we suddenly use 500 megahertz, or 10 megahertz, 1 megahertz, whatever. So we spread the signal. I will explain how we do this. Why do we do this? Well, the basic idea is that if you spread out your signal and you have narrowband interference, the narrowband interference only cancels out a small fraction of your signal. I will give you an example for this. So instead of putting all the energy in the narrow band, we spread all the energy over a larger band. That sounds simple, but you have to develop the transmitters for this, the receivers for this, etc. Without telling you right now how we do this, well, okay, it protects against narrowband interference. Why? In the end, for the signal, yes, if you cancel, let's say, 1 or 2% of the signal, on the receiver side it doesn't matter. You can still reconstruct the original data. You receive enough energy because you need a certain amount of energy to transmit data. So to transmit a single bit, you need a certain amount of joule, picojoule, atto, femto, whatever, just a little bit, but you need energy. So the receiver has to receive energy and then has to decide, was this a 0 or 1? But it doesn't matter. If you spread this energy over a larger fraction of the frequencies, a larger part of the spectrum, or a smaller part. So stronger signal over smaller part, weak signal over larger part. So we can protect against narrowband interference. I will give you an example. There are nice side effects. So I will show you that we can have many signals without any coordination coexisting. Same frequency, same time. That sounds like code multiplexing. Yes, spread spectrum is a technology you need for code multiplexing. I will show you how. And the nice thing is, if you don't know how someone spreads the signal, you will only receive noise. So that's also something I will show you. And there are two different ways, direct sequence and frequency hopping. That's how you spread the spectrum. Okay, so step by step. First of all, what is the effect? So we start with a narrowband signal. So this is now the user signal. Now let's say, for example, you have a wireless LAN channel operating at 2.4 and then blah, blah, whatever megahertz. And usually those channels are only, now let's assume 20 megahertz. 20 megahertz. So, well, it depends on if you call this narrowband, but now let's say this is a certain amount, let's say 20 megahertz. And you need a certain, well, amount of energy you put into this to transmit your bits. So that's a strong signal, okay? So what you do now is you can spread this. How? I will explain. So basically, instead of sending, let's say, 10 megabit per second, you can send 1 giga symbols, chips as we call them, per second, spreading your signal. What happens? So basically, all the energy you have here in narrowband is now put into this wideband signal. The area in this rectangle is the same. The area represents the energy you put into your signal. Now you spread it out. Okay? You spread it out over a larger frequency. Now, maybe we go, doesn't matter now, from 1 to 100 megahertz. No matter if this is allowed or gigahertz. Gigahertz. Giga, mega, doesn't matter for this example. If you now have a narrowband interference somewhere here, what happens? It will cancel out a part of the signal. So what happens over the air? So this is our, on the center side, and now over the air, we generate a nice signal, which is our spread user signal. In the air, or in space, we add noise, background noise, broadband background noise. That's always added. So we have a broadband interference. Broadband interference here, that's the broadband interference. Plus, in this example, we have our narrowband interference. That's our narrowband interference. Now in this example, it's really maybe extreme, killing part of our signal. So that's a narrowband interference. Now the magic thing happens, and I will also show you how. On the receiver side, we can despread the signal by using certain algorithms. I will show you a simple example for this. We despread it, so first we spread it, and then we despread it. And what happens is, only the user signal spread in a certain way can be despreaded. The broadband interference will remain spread over all the whole spectrum. And the narrowband interference, which is not coded in a certain way, will then be spread out over the whole, over a certain amount of the spectrum. So broadband stays broadband interference, narrowband becomes broadband or broadband interference, and only the user signal can be actually reconstructed in a kind of a narrowband. Then the next step is you use something called a band pass, a filter that cuts off certain frequencies. So what remains is a narrowband signal composed of the original user signal plus a fraction of the broadband and the narrowband interference. And now the hope is, if the interference is not too strong, you have enough energy left in this dark area to reconstruct the original data. Because as I told you, need a certain amount of energy. So that's the idea, that this is still enough for the receiver to reconstruct the 0 or the 1. So that's a very simple way spreading and despreading explained. And that's exactly what many of the systems of today do. For commercial systems, you can still actually see that someone sends something here. So you create a certain amount of noise. For military systems, spreading factors, that's we call the factor, how much is spread, are 10,000, 100,000. And you can even spread in an extreme way that the signal level is lower than the so-called noise floor, the noise level. Then you cannot even detect that there's a signal. So you can hide your user signal in the noise. It's just a question of how much noise do you have. So if you have a certain noise level here, so if this is our noise level, then you can hide the signal. No one will notice that you transmit something, which is a good idea if you are in a hostile environment. No one should actually notice that you transmit something. Otherwise, you use a spectrum analyzer and you check the spectrum, and if you have some peaks, you know, there are some senders. Okay, and then you can use triangulation, etc., and then you can find the source of the signal, and then send some nasty rocket to the source, etc., etc. So that's what is done currently. This is why no one in these regions uses mobile phones or whatever. This is way too dangerous. Okay, so, but if you hide your signal, no one sees it. And then in addition, if you do not tell anyone how you code your signal, even if you receive the signal, you cannot despread it. So this step of despreading here works only if you know the code. If you do not know the code in this step, you cannot despread the original user data. So first, you hide it, and second, you use a secret code. And that's it. And that's exactly what you do for military transmission systems. So you cannot receive them, and if you receive them, you don't know the code, and that's it. So you can hide it. So you can even hide these signals in the background of analog, digital TV, our mobile phone systems, whatever. So you can simply spread it. It's a different question if this is allowed for commercial, civil use, etc. That's something different. The civil systems, like a wireless LAN, like UMTS, whatever, stays within the limits given by the regulation. So a normal wireless LAN system is not allowed to use 1 gigahertz here and there of the spectrum or whatever. No, you have to stay within the limits, but depending on how you use it. And if you do not tell anyone this secret code, and this is what you also can use in mobile phone systems, you cannot receive it. There's no simple way of receiving. Or frequency and time division multiplexing, you can easily tap, so it's simple to follow all this, so like Bluetooth and whatever. So you have to encrypt it, but this is a very basic way of encrypting your signal. You can't even receive it because you cannot despread it. So that's a nice technology, but you see how all this is coupled. Code multiplexing, spreading, you use a special code for spreading, and this brings a signal into this noise, and then you can use many signals. Yes, they all contribute to the noise. Yes, there must be a problem with this. I will come back to this problem. Okay, but that's the idea of spreading. Yeah.
If your signal is not distinguishable from the noise, how can you even receive it or receive it?
Good question. How do you see the signal if it's not distinguishable from the noise? The point is, you receive everything. So broadband, receiver, that includes the noise, that includes all the other signals. So it's this mishmash of different signals. And to this chaotic whatever signal, you simply apply the despreading algorithm. And then, that's the magic part. I will give you a simple example for this. You have a nice correlation. There's where you can see suddenly, by this despread signal, the certain peaks, because only using the right code to this complete mixed signal will result in a more or less original unspread narrowband signal. That's a tricky part. I will give you a simple example for this. If you want to read more about this, Andrew Viterbi is one of the founders of Qualcomm, and they did a lot of pioneer work in CDMA. So Viterbi, and that's explained how you do it, what kind of codes to use, what is the quality of the signal, how you generate these codes, how you do spreading and despreading. This is a ultra simplified, lightweight version, because only looking to code division multiplexing would I give an extra course. This is and the book by Viterbi is thick, and there are some more. So Andrew, that's just one example. Andrew Viterbi, that's one, and the company Qualcomm, they are still big in business with mobile phone modems. They did a lot there. So indeed, you receive everything, including noise, including everything, and you perform the despreading without knowing what's in there, and that's the magic part. I will give an example that you can find out the original code. Only the, so to say, the original spread user signal reacts to this code, if you know it. Then it's a question, how do you synchronize, how do you this and that? So it's not that simple, but that's the basic idea. But yes, good question. What do you receive? So you don't know it. So basically, instead of tuning into a certain frequency, you have to tune into certain codes, apply them, and then try to receive something. And, well, you have the right code if the bit error rate is low. You will have some bit errors, but that's the only way to find out. You try to apply the code, and if you receive something meaningful, that means low bit error rate, yes, then you have the right code. If not, then not. Okay, so what is, first of all, the big advantage of this spreading? So the classical systems use narrowband, like shown here, narrowband channels. And here if you have a certain channel quality, shown here with this black solid line, a certain channel quality at a certain point in time, then you see, okay, well, too much interference for channel 4, too much interference, I guess, also for channel 3. Maybe there's a certain threshold, at least the signal should be stronger or above this red line, for example. So, channel quality too low for 3 and 4. What you do with this spreading is basically you spread all these channels, so there's 1, here's 2, 3, up to 6. You spread them over the whole spectrum, and now the channel quality is the same. It actually distorts part of the spectrum here, but the hope is there's enough energy left in the remaining parts of the spectrum that you can reconstruct the original signal, which means the original data. That's the idea. So that's one of the first advantages. So spread spectrum technology, well, you're not that vulnerable when it comes to frequency selective fading, because sometimes it happens that certain frequencies experience a lot of interference. Okay, like the classical microwave oven, 2.4 gigahertz, something, and then you're lucky if you have more of the spectrum. So that's one thing. And also, if someone wants to, well, disturb your communication, then sure, you try to jam certain frequencies. That's what's done, for example, if you have some politicians entering certain areas, they're automatically, you use jammers to jam certain frequencies, usually used to whatever, build explosives, do this, do that. So you jam the frequencies. That's the first thing you do. And there are some very efficient frequency jammers. So some military frequency jammers, you cannot transmit anything but the special military, well, spread signals. Okay, so that's what's done usually if you have whatever president of some country arriving, then you block certain frequencies, the classical GSM and many others. So how do we do this? So big advantage, frequency selective fading. But how do we do this? And a very simple way of doing it is a fully digital way. It's called the direct sequence spread spectrum. So basically what you do is you perform an exclusive OR. So an XOR, so first of all we have our user data. User data, so we want to transmit one bit which is 0, one bit that is 1. A 0 and a 1. And then we perform an XOR with something that is called a chipping sequence. So we XOR the 0 with these 7 so-called chips. Here you have 7 chips. We XOR it. So we XOR 0 results in 0. 0 XOR 1 results in 1. 0 XOR 1. So you see this is the original chipping sequence, and with 1 you invert the chipping sequence. So what happens now? The resulting signals has now 7 times more chips compared to original bits. So this is why our spreading factor in this case is 7. And if we now use the same digital modulation scheme we can use for the original data, we expand the spectrum we need by a factor of 7. Because we have 7 times more potential changes in our chips, bits, and then depending on how we code it, frequency or amplitude or phase shift. So we spread our signal. As you see, we need here more of these symbols to transmit the resulting signal. So it automatically spreads it out, which is a disadvantage because we need more bandwidth. But we saw the advantage. We are not that vulnerable to frequency selective fading. So, and that's the idea and the big advantages. For example, UMTS, the third generation of mobile phone system, uses such a technology. So all your mobile phones, if they operate in 3G mode, they all work on the same frequency. It's the same frequency if you are with the same network operator. So all the base stations, as we will learn, can use the same frequency. So that's very simple. And we can perform something you will not understand right now, but later on, things like so-called soft handover, and we can use same frequencies also for many different base stations, which makes many things simpler. But as we will also learn, we need very precise power control. I will explain this disadvantage together in the context when I explain how we do this, what this code means. This example will come in a few minutes. So, precise power control for UMTS for the mobile phones using third generation. This means 1,500 times per second. We have to control the output power. That means 1,500 times per second, the base station tells your mobile phone send stronger, stronger, weaker, weaker, stronger, weaker, 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 stronger, stronger, weaker, weaker, weaker. 1,500 times per second. Because, I will explain in a few minutes. So, yes, it's nice. You see, this is one way of doing it. So we are putting together these building blocks for the mobile phone systems. So now you know how you can spread using the so-called direct sequence spread spectrum. And this alone fills a complete course in the book, how you can do this. And you will learn why this is why there are also some disadvantages when it comes to power control. But it should be clear, if you transmit these bits, you need smaller fraction of the spectrum compared to this where you transmit 7 times as many bits, not called bits, but called chips now. Chips. The bits, that's what this term we use for the user data, with a certain bit period, and then with a chip period, which in this case is only a fraction of this bit period. Okay, that's one way of doing it. And so what you do in the end is you use your user data. These are our bits. We use the chipping sequence. And this is a full digital way of generating the spread spectrum signal. Then we have the spread spectrum signal. And then we can perform all this modulation transmitted. And then we do the analog part, the demodulation. And then we do the magic part. I will explain in a simple example. This is the not so easy to understand magic part. We will see an example for this. Okay, so that's the basic building blocks. So you use your bit sequence, then you chip them, and then you have your chipping sequence, and then you perform your shift keying and modulation, shifting, maybe, etc., depending on the signal, what you generate. But the tricky part is really how can you simply receive all these mixed signals, exactly as the question was, how can you receive your own signal out of this? That's where I give you an example. There's also another way of creating this. You can look into it, so-called frequency hopping spread spectrum. So the idea is that instead of applying a digital XOR to the user data, you start jumping through frequencies. If you do it fast enough, you basically also create a larger spectrum. That's the idea. And so you can also avoid this frequency selective fading because you remain on a certain frequency only for a short period of time, then you jump to other frequencies. And if you do this fast enough, the interference on a certain frequency hits you only for a short period of time. That's the idea. Okay, well, the implementation is simple. This is why, for example, Bluetooth uses this. It's a very simple scheme and not as robust as direct sequence, and it's simpler to detect. What you do there? So if you transmit your user data here, you can perform a so-called slow hopping. So that's one thing. So you stay on a certain frequency, carrier frequency F2. You transmit our 0, 1, 0 on this frequency, and then you jump on another carrier frequency. That's called slow hopping. You transmit several bits in this case per hop. That's what Bluetooth does. So Bluetooth remains for 625 microseconds on one frequency, transmitting many bits, and then jumps onto another frequency. Only it looks fast for you, this doesn't mean it's fast hopping, so it's slow hopping. And fast hopping means within a single bit, you jump already F1 to F3 to F2, whatever. So that's a fast hopping scheme. Because you use many different frequencies, several frequencies for a single user bit. Usually the systems like Bluetooth, even GSM can use it. They perform slow hopping. So they transmit many bits on a certain frequency, then they switch to another frequency, transmit many bits there, switch to another frequency. Bluetooth uses this to implement a multiplexing of different networks. So Bluetooth creates networks, and maybe in this room we have several Bluetooth networks, and we want to avoid interference. So each Bluetooth network has its own hopping pattern, and we hope that there's only very short overlap. And if there's overlap, yes, then we have interference. That means bit errors, tough luck, but usually we don't have overlap. That's the idea. So that's also a way how you can create a spread spectrum. You jump through many frequencies over time. That means you use a larger spectrum. Only a small part of the spectrum at a certain point in time, but over time you use a larger spectrum. So direct sequence and frequency hopping, those are two ways of implementing this spread spectrum technology. And again, that's just this very simple block scheme, how you do this modulation and how you do this hopping sequence, etc., etc. And now the question is, and this is exactly what we learn in Bluetooth, how do we learn the hopping sequence? So if you do not know the hopping sequence, that means how you jump through frequencies, it's very difficult to follow someone. Yes, I mean, if you receive everything, and then if you have a signal processor, then you can check basically and you will find out. So it's not something against eavesdropping, but it tries to avoid interference. And in Bluetooth, we will learn how a so-called Bluetooth master tells the Bluetooth slaves the hopping sequence. And then, if you know the hopping sequence, you can all hop at the same time, and all the devices in the network can follow each other and can transmit data. So that's another scheme. So frequency hopping spread spectrum. Okay, but for most of the technologies we'll look into, they use a direct sequence because this is a digital technology that's much nicer, much simpler to handle. Okay, and now something that also fits quite nicely here. You saw we can play with many parameters. Parameters like phase, like amplitude. We can perform spreading. We saw a digital way of spreading this direct sequence spread spectrum. And many years ago, that simple idea popped up that said, okay, why can't we create the complete real signal we transmit over the air already in a computer, in a full digital way? We know the algorithms, how we can create arbitrary signals. That's an algorithm. We know how to spread, how to despread, how to encode, decode. We know how to create amplitude modulation, how we can change the phase, etc. It's just a question of algorithms. Okay, the computers have to be pretty fast. So already many years, if you go back to the classical GSM system, a classical mobile phone with a chip that generated all the signals. If you replace the chip by a computer and try to do this fully digital, you needed already at that time tens of thousands of MIPS, so quite powerful computers training your battery within milliseconds, I guess. So not a good idea. So VLSI sometimes is a good idea to create your own chips. Much more energy efficient. But over time, we had more powerful processors, especially so-called signal processors. And the idea there is now, and that's the key idea behind software defined radios, that you have an application generating user data, and then the signal processor basically downloads modulation scheme, carrier frequencies, coding, all these things, downloads over the air. All this, if you enter other country, or you want to use another network operator, or complete different technology, you say, oh, what is this? Oh, this is some whatever wireless LAN according to 802.11bx standard. I don't know what this means. Okay, let's download the code. Oh, suddenly I can do all the modulation and everything. Because everything is now handled in the signal processor, generating here already, well, it depends on the frequency, something like, now let's say, for example, 60 gigabit per second. And all you do here is, you do a digital to analog conversion. Okay, that's also a problem today, because 60 gigabit per second digital to analog conversion, that's expensive. That's just the idea. This is why we are not there yet. That's the ideal world. So we simply download a new radio. Not only a new app, but download a complete new radio. Today, we need, for example, FPGAs, field programmable gate arrays for this, so specialized programmable hardware. We have key components in hardware, and you can actually program them. And they're available together with DSP signal processors. So the combination of the signal processor, a general purpose processor, plus an FPGA almost creates something like a software-defined radio. But that's the idea. Ultra-fast digital to analog conversion, and on the receiving side, you have ultra-fast analog to digital converter, converting everything you receive from 0 to 100 gigahertz, everything. Okay, that means Nyquist, Shannon, 100 gigahertz, okay, this should be 200 gigahertz fast. Okay, that's a lot, but in theory feasible. You generate your data stream out of this, etc. You have your nice data stream. You have to be fast, okay? And then you have all your user data for the application. The problem is, yes, high data rates. We need amplifiers. Up to now, we cannot build them. Amplifiers, low noise amplifiers that amplify from more or less 0 hertz up to 100 gigahertz. They do not exist. So there are broadband amplifiers, but okay, filters, okay, there are some real world problems. If we ignore them, that's nice. So, but what does exist? There was I'd say 10, 15 years ago, the first approach, Joint Tactical Radio System, that's a military system, GNU Radio, the Universal Software Radio Peripheral, etc. So if you want to look into this, there are nice articles. You will find the KVB in the resources about SDR 20 years later. Some nice articles. Where are we today? So we are not there yet in the ideal world. So there are some problems, real world problems, because in the end, it's way too expensive if you want to create this very general purpose system. But if you invest something, I'd say, let's say, that's already a nice system, 500 euros, then you will have a nice, almost free programmable software-defined radio where you can create your own GSM base station, UMTS system, or receive whatever there is between the usual ranges, some 100 megahertz up to some gigahertz, something like this. So they are available, not the ideal software-defined radio, but at least for the normal systems you can easily buy them. There are even cheaper versions. If you only want to receive something, then you can use these classical DVB-T receiver sticks. You can reprogram them. That's very cheap. That's pretty cheap. But if you also want to send something, then you have to invest a little bit more money. But be aware, illegal. Okay? Not legal. So at least if you play with it and you do not use a power amplifier, and you are not allowed to really transmit it, then you can play with it, install, etc., but you're not allowed to send on all these frequencies. Just because something is feasible, it doesn't mean it's legal. Okay, so, but it's very nice to learn a lot about how all these different schemes work, etc. If someone is interested in this, come to me and we can easily get to some of these systems and you can do whatever bachelor, master thesis with this. It's quite interesting to see because you can learn a lot implementing your own base station. What does it mean? Blah, 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 all these things. So a lot of software is available. So the whole software for base station, the whole GSM stack, everything is open, etc., etc. So interesting. So you see, within some years, we will have complete flexible devices and no one will ask, oh, is this a fourth or a fifth or whatever generation system? We will simply download new codecs, new modulation schemes, new radio schemes, whatever. So we will see this, let's say 10 years from now, 5, 10 years, 15 years from now, at least we can download parts of it. Not yet, there yet, but soon. Okay. And then we're still at this very, very low layers. Just to complete this, in the next chapter I will explain how all these fancy things work. But here, just to give the complete pictures, in the end, we started with antennas, simple antennas, and what, together with especially the GSM system, came up was a so-called cell structure. Why? Well, I showed you with space division multiplexing, we create transmission ranges looking similar to this, well, maybe rather like this. Doesn't matter, but as long as we have guard spaces, we can reuse, even with the classical technologies, we can reuse the same frequencies at the same time. So that's one reason why we create cells. Cells, that means we artificially create a certain transmission range. Then we know we have the interference, etc., different detection ranges, interference ranges. A second reason is, well, we have higher capacity. Imagine you have only 3 cells, only 1 cell in Germany, with all the mobile phone receivers. And let's place the antenna in Frankfurt, for example. This must be an extremely powerful antenna, but still, well, it's limited when it comes to the overall capacity. Maybe you can handle 1,000 users, but that's it. But today we have millions of users, and we can only handle this if we have more and more smaller cells. So this is, if you want to have a higher number of users, we need more and more cells. Plus, if we have smaller cells, we need less transmission power. It's more robust. So if, for example, a cell breaks down, it doesn't matter. Why? Because for cities, we have many small cells, we can easily hand over to another cell because they are overlapping. Plus, we always have something called an umbrella cell that covers a larger area. So if you drop out of a cell, you can automatically be handed over to an umbrella cell that covers a larger part of the town with a stronger, larger antenna, more transmit power, but with an overall less capacity, so you cannot handle the whole town with one umbrella cell, but at least for all those subscribers dropping out of a smaller cell, you can handle them before they re-enter another cell. So that's one of the ideas, and also you can much better deal with local interference. If you have smaller cells, you can switch the channel, etc. If you have one huge cell all over the country, it's very difficult. It's very, very difficult to handle interference. Yes, as soon as we introduce cells, you can imagine, okay, we have many of these overlapping cells, and you're moving through the cells, we have to, well, take care of the handover. If you move from one of the cells to the next cell. That's something we look into when we come to the mobile phone system. You have to take care that we do not have interference with other overlapping cells. So in the classical technologies, use a different frequency. So there are some problems. So today we use these cellular systems. This is why in many countries it's called a cellular system, mobile phone system, cellular system, with some small cells, 50 meters, 100 meters radius. And for example, on the countryside, less density, less population, something like 35 kilometers for GSM, maximum distance from a mobile phone to a base station. I will explain why this is 35 kilometers. This has nothing to do with the transmit power. We could easily, whatever, bridge 60 kilometers or whatever. This has something to do with the time-slotted nature of the multiplexing, the multiplexer scheme. So if you move further away from a base station, you cannot be synchronized with the system anymore. So that's one of the technologies used in GSM, so 35 kilometers. But that's just example. So here downtown, we have some 100 meters, sometimes 50 meters, depending on whatever the population, how many subscribers per square kilometer do you have. So downtown, many, many more compared to the countryside. All over, this creates a structure quite often shown with these hexagonal patterns, like a honeycomb. And this shows how you can reuse frequencies. So you can reuse frequency shown red here and the same frequency here. So because you have at least two cells in between, so even if you have some more bizarre shapes for these cells, in real life they never look like this, it's just shown like this because it's nice to draw, you can reuse the frequency. And you can do many interesting things here. You can adjust the number of frequencies or channels available in the cell depending on the load. So you can say, okay, usually we have, for example, 5 channels per cell, something like this, for example. But if there's a big event in some of the cells, we reassign some of the channels from the neighboring cells to this cell. So you borrow some channels. That's one of the ideas. So depending on the load, well, if you have more traffic, you also have more capacity because you can borrow some channels. So based on interference, based on planning, whatever. So the classical mobile phone technology, the classical wireless LAN technology, they all use these cell structures with frequency planning because they use frequency multiplexing with GSM, with wireless LAN. Many of those systems, you have to do frequency planning. Not with the third generation, there it looks different because there we use code division multiplexing. But here with the classical system, you have these cells, and then you go into the frequency planning. Then you have 3 cell clusters and whatever cell clusters and sector antennas. That's exactly what you quite often have. You see this antenna pole, and you see these slightly tilted 3 antennas, whatever. with each 120 degree, covering then the 360 degree, something like this, the main lobe of this antenna, then slightly to the downward towards the road. That's just one example with the sector antennas. And there you have to do all the cell planning. That's exactly what the mobile phone operators do, all the cell planning. And in Germany, we have about 60,000 of these base stations, 60,000 of these antennas. We have way more, but these are the big base stations. We have way more replicating the signals. For example, if you go in the underground, we have special antennas there that you can use your mobile phone in the underground, etc., etc. But something like 60,000 of these antenna sites we have. So, and there it's quite complicated to the frequency planning, to avoid interference, etc., to borrow channels, to do all this, to be also a little bit dynamic. Okay, and because this is complicated, some of the operators were quite happy to see the third generation, some years ago, almost 20 years ago, where we use codes to multiplex different uses. There we use frequencies, and as you will see, also time to separate uses. But with third generation, as I will show you, we introduced code division multiplexing, and that means, well, we can use the same frequency, which makes it much simpler, this planning. Well, you first think of the cell planning, it makes it simpler, because we don't have to take care if we use the same frequencies here and there. We always use the same frequency. So we only have to make sure that you have a good signal quality all over the place, but we all use the same frequency. How the separation is done? Next chapter. One problem there is with the code division multiplexing. That's another term you should remember, the so-called cell breathing. Why? Well, I told you, basically, it's the way that you have your narrowband signal, and you spread it. So you spread it. But many do this. Many do the spreading. So in the end, over the air, you have many of these spread signals, and they all contribute to the noise. So it's like when you all start talking, you all use the same frequency. So you all, in the end, if you're not interested in the content, you all contribute to the noise in the lecture hall. Okay, now let's assume I'm the base station here. So that's me. And now you want to transmit something to me. We do this code division multiplexing, and you're not interested in the content, but you all contribute for now to the noise. So what happens? Now, if you all start talking, just a little bit sending some voice, whatever, that's okay. So I, as a base station, I'm able to receive it using this code division multiplexing, this magical thing. And for all the others, so the conversation appears as noise, because if you do not know the code, it's noise. Okay, but what happens if someone, for example, sends more data? We need a certain amount of energy to transmit a certain amount of data. So, if you now translate it in my example here in the lecture hall, if someone of you starts talking more and more, or a little bit louder, so that I receive everything, more bits. Then suddenly, the problem here is that for all the other devices, this is like noise. To be still heard, they also have to talk louder. All the mobile phones have to increase the output power. There's a certain upper limit. So, if we have a strong sender, like someone closer to me talking loud, all the others, they try to send with their maximum output power, but sooner or later they will drop out. I cannot receive them anymore. They're too far away. And that's one of the problems with all these code division multiple access and code division multiplexing technologies. If you are further away from the receiver and all the devices have the same maximum output power, I will in the end only receive the devices closer to me. we will learn that this is called the near-far problem. And so it looks like all the devices at the edge of the cell will drop out. They cannot communicate anymore. It's like someone in the last row. If everyone is talking very loud, I will only receive those of you in the first 1, 2, maybe 3 rows, but not those in the last rows. So, that's a problem. And it's called cell breathing because it looks like the cell is shrinking if the load increases. It's not really the cell is shrinking, but the devices at the edges, they drop out. And if you stop the transmission, then suddenly the cell is growing again. It looks like breathing, because then the output power here is, in the end, it's strong enough to send again. Okay, so that's the basic idea. If you stop sending, then suddenly it's strong enough and you can send and receive again. And this problem of breathing cells is not easy to handle. With the CDM systems, we do not have to plan the frequencies, but this highly dynamic behavior is even more complex, because you can imagine during peak hours in certain roads, suddenly the cell sizes shrink and suddenly you lose the connection to your test system. Hey, the signal quality was nice. What happened? No change in weather. I did not move. But why is suddenly the signal quality worse? Because many others use the same system. So you need additional mechanisms to control the access to these systems to more or less avoid this cell breathing. You cannot really avoid this because that's physics. So the cells in these systems, they will always shrink and grow and shrink and grow. So you have dynamic cells, which makes planning a little bit more complex, as you can imagine. So cell breathing, it's an interesting effect. We will come back to these very basic effects, multiplexing and breathing and cell planning, etc., when I explain the technologies, the mobile phone systems, second, or third, and a fourth generation to you. Then we will come back to this basic technology. We are still down there at the signal level, not there yet. Okay, so that was more or less all I wanted to tell you about signals, signal propagation, characteristics of signals, and some more fancy things like cognitive radios, like software-defined radios, etc. We will not go into more detail when it comes to all these more electrical engineering topics, because this should be computer science, and I still want to have enough time to explain you more the protocol sides and how to handle mobility, the higher layers, and how all these complex systems then work. Okay, that's it for chapter 2. Do you have any questions in any language? Okay, so please do look into at least these key issues of what happens to signals, why spreading, what is cell breathing, what are these effects. You should at least understand them on this, let's say, a little bit more abstract level, which is okay and enough to understand the basic characteristics, then to understand why do we have such strange TCP behavior on layer 4? Yes, because, for example, your data rate varies a lot because of cell breathing. That's nothing the creators, designers of TCP took into consideration. Yes, it will be 40 years from now also be used by co-division multiple access technologies. No. How does TCP react? Strange. Because we'll measure round trip times and data rates and all these things. We will see. So, okay, so that much.